our strategy will be to leave the inclination alone for the moment, because we saw how big a cost it would be to fix that, to drive that to zero right away, is 3.839 kilometers per second in equation 12. So let's not do that. Let's instead perform the first half of a Hohmann transfer so that the apogee will be at the radius for a sidereal period orbit. Now, how do we calculate that radius? Well, the orbital period of a circular orbit can be calculated by dividing the circumference of the orbit by the velocity, right? So we have distance traveled, 2 pi r, divided by the circular speed, square root of mu over r. And if we take this r, which is to the minus 1/2, and bring it upstairs, we have r to the 3/2, and we have still a square root of mu downstairs. And we can rearrange. Well, here we have r, of course, to the 3/2 inside the square root and square root of mu. We can rearrange this equation to solve for r, and we get r is the cube root of period squared times mu over, we squared the 2 and the pi, we had 4 pi squared. So rearranging, we can solve for r, and we're going to put in then the period of interest into equation 14. One sidereal day is 23 hours, 56 minutes, 4 seconds. If you add it up, you get 86,164 seconds. The mu of the Earth is 3. This is, of course, the GM, Newton's universal gravitational constant times mass, which we combine into one gravitational parameter called mu. And the value for Earth is 3.986 times 10 to the 5th kilometers cubed per second squared. And we plug this value into equation 14. And we plug in the time in seconds. We notice that here we have seconds squared, and multiplying by inverse seconds squared get rid of the seconds. And we have non-dimensional terms downstairs. Radians is non-dimensional. We can ignore radians when we want. And upstairs we have the cube root of kilometers cubed. So we're going to get kilometers out of our answer. And the answer for a geostationary orbit is 42,164 kilometers from the center of the Earth to the radius of the geostationary orbit. Now we can calculate the velocity change maneuver, delta V1. That's the first half of the Hohmann transfer, which is given by delta V1 square root of mu over R1. So R1 is the first orbit radius. And then square root of 2r2. R2 is the second radius over r1 plus r2 minus 1. So in our problem, the radius 1 is the 176 kilometer orbit plus the radius of the Earth to give us 6554 kilometers. And we just calculated the radius for the geostationary orbit to be 42,164 kilometers. So plugging all this stuff into equation 19, we get down here in equation 22 with the numbers. Here's the mu of the Earth. Here's radius 1. Here's radius 2. Radius 1 plus radius 2. So plugging in, and by the way, this first term, the square root of mu over r, is the circular speed at r1. And then we multiply by this fraction, 0.3157, and get the delta V1 is 2.462 kilometers per second. Now this maneuver should be executed at the node and should not change the orbital inclination. So here's a sketch. We're performing this delta V one here. Assume that we have started in a circular orbit that's inclined. So let me just sort of sketch that in here. So we start in a circular orbit. We launch from Cape Canaveral, sort of on the other side of the Earth here, and we ended up in this inclined orbit of 28.5 degrees. And now we want to do a delta V1, which is along the direction of the circular speed we had, and that'll carry us out on this elliptical orbit, and we are always in that inclined plane here. And when we cross the equatorial plane, this point is called the node. We left from a node here as well. And in fact, here's the line of nodes. It's the intersection of the two planes. When you have the intersection of two planes, you have a line. So you have the inclined orbit plane, and then we have the equatorial plane. The intersection is this line of nodes. And if you want to zero out the inclination, you have to be on the line of nodes. You have to be in the equatorial plane in order to zero out inclination with an impulsive delta V. So when we get over here, this is the place where we could zero out the inclination. We're traveling in this direction in the inclined orbit, and we want to get rid of the sort of the vertical component of that.